If you're new to solving Aime problems, you are probably unfamiliar with the concept of a radical axis. So to begin our introduction, let's define the power of a point, say P, with respect to a circle, say circle O, is the square of the distance from P to the center of that circle minus the square of the radius. In particular, if P is on the circle, then the power of the point P is equal to 0. If P is inside the circle, then the power of the point is negative. In particular, let's describe the set of points P such that the power of that point P with respect to one circle is equal to the power of that point with respect to a different circle. We call this locus of points the radical axis. Let's put the centers of our two circles on the x-axis and find these distances. We want PA squared minus the radius of circle A squared to be equal to PB squared minus the square of the radius of circle B. Using the distance formula, the distance from P to the center of circle A is x minus a squared, and because the center of circle A is on the x-axis, we can just say that the vertical distance is y squared. Subtract the radius, the square of the radius of circle A, and likewise with the distance from point B to the center of circle B minus the radius of circle B. Expand our squares and combine like terms and solve for x. We find that the y terms disappear and we're just left with x is equal to an expression in terms of a, b, the radius a, and the radius of circle b. And these are all constants. So what we have is x is equal to a constant. This is a vertical line. Let's say our two circles intersect at points Q and R. Because Q is on circle A, the power of the point of Q with respect to circle A is 0. And likewise, Q is on circle B, so the power of the point with respect to circle B is also 0. Similarly, for point R, both of these points are on the radical axis described by this equation. So we have that this is a vertical line that passes through the points Q and R, the intersecting points of our two circles. Next, we're going to show that the radical axes of three circles are concurrent. Let's let AB be on the radical axis of circles 1 and circle 2, and CD be on the radical axis of circles 2 and circle 3, and let's let their intersecting point be Z. If Z is on AB, then the power of Z with respect to circle 1 is equal to the power of Z with respect to circle 2. If Z is on segment CD, then the power of Z with respect to circle 2 is equal to the power of Z with respect to circle 3. This equality is transitive, so the power of Z with respect to circle 1 is equal to the power of Z with respect to circle 3. Therefore, Z is on EF, which is the radical axis of circles 1 and circle 3. And so all three radical axes are concurrent. Sometimes the overlapping circles don't produce nice football shapes, but just look for where the two circles intersect. Join those 2 points and you'll have a radical axis. Let's return to the problem. We have a couple of overlapping circles with a common tangent. D, Y, and C are collinear. I'm going to draw the radical axes by connecting these intersecting points. Let's call the point where they intersect point C. First, I'm going to show that quadrilateral ZAXB is cyclic. We have two other cyclic quadrilaterals, AXDY, which is on this green circle, and BXYC, which is on the brown circle. The opposite vertices of these two quadrilaterals add up to 180 degrees. For AXDY, that's angle D, and this other angle AXY. And then for the second quadrilateral, that's angle C and angle YXB, or BXY. Both of them add up to 180 degrees. We're going to add these two equations. We note that angle AXY, BXY, and AXB together form 360 degrees. So we're going to make that substitution. Sorry, I forgot to include this angle D up here. Angle AXB equals angle C and angle D. Take a look at triangle ZDC. By the angle sum, we have angle C plus angle D is equal to 180 degrees minus angle Z, so we'll make that substitution. And we have opposite angles of the quadrilateral add up to 180, so the quadrilateral ZAXB is cyclic. Let's look for some congruent angles. First, let's take a look at cyclic quadrilateral AXDY. If we take a look at arc AX, we note that the inscribed angles that cut off arc AX are angle ADX, AYX, and this tangent angle BAX. We'll call that angle alpha. We know that quadrilateral ZABX is also cyclic. I'm not going to draw the circle, but we can see that angle BAX is an inscribed angle of that circle. And similarly, angle BZX also cuts off that arc. So those two angles are also equal to alpha. Similarly, with the other circle and cyclic quadrilateral BXYC, when we take a look at the inscribed angles that cut off arc BX, we have that the inscribed angles are BCX, BYX, and this tangent angle ABX. Let's call these three beta. And similarly, when we consider cyclic ZABX, and we note that the inscribed angle ABX cuts off arc AX, then we have that angle ABX is also equal to angle AZX. So that's also equal to beta. We have a lot of congruent angles, so let's look for some similar triangles. We know a couple of side lengths, and a couple other side lengths are common. So we have XZ is the square root of 67 times 37. Let's take a closer look at quadrilateral ZAYB. I'm going to draw it separately, and I'm going to fill in those congruent angles. Notice that angle Z and angle Y of this quadrilateral are congruent, so we have a parallelogram. Let's let point M be the intersection of YZ and AB. Because this is a parallelogram, M is also the midpoint of these two diagonals. We have a couple more similar triangles, triangle ZAY and triangle BXA. I'm also going to draw in the medians. So AM and XM are medians, both medians of these two triangles. Corresponding sides, AM over XM is equal to YZ over AB. We're going to make some substitutions. First, AM is half of AB. Since YM is equal to ZM, we rewrite these in terms of XY, XM, and XZ, so we can make some substitutions. So far, our ratios look like this. And we have finally that YZ is equal to XZ plus XY. So let's make that substitution and solve for the square of AB. Difference of squares, and we substitute with the values that we know. When we compute, we get the answer.